Hi, everybody. I'm Kara Phillips, and I'm excited to join you for this presentation today on the SPIR-Ace with quantitative and spectroscopic analysis. I hope this presentation will be about 45 minutes in length, and I encourage you to give questions throughout the presentation. At the end of the 45 minutes, we'll go through those questions and answer as many as we can, and if you have even more, we'll answer those offline. What we're going to be talking about today is the SPIR-Ace with quantitative spectroscopy. The SPIR-Ace itself has been around for a few years now and is really originally intended to detect, locate, identify, and now this additional feature called GenieXport that we're adding is to quantify, to determine that quantitative analysis with this device as well too. And so that's for me really exciting. The original version, the primary SPIR-Ace, it's a really nice versatile identifier, primarily for homeland security and other applications to quickly be able to find those activities or find those sources of radioactivity and identify what that nuclide might be. When we now add that quantitative component to it with what we call GenieXport and ISOCS characterizations, we now make it an option for really great in situ measurements that have a really nice modern interface and other functionality that we're excited to share with you today. There are a couple of key features. One, the device itself is available both with a sodium iodide detector or for those nuclides or spectra that might be a little bit more complex. The lanthanum bromide with higher resolution might be a better option as well too. It does satisfy many international regulations such as ANSI N482 and IEC 62327. One of the really key features about the device itself is that even on board, it really has a very rapid nuclide identification. Just within a few moments here, and we'll show a few examples, you'll be able to check up to 80 different nuclides using 7 different customizable user libraries. Another nice feature is the fact that it does have an active energy stabilization, such that if the device goes into a very hot area, the device will automatically self-calibrate to keep that gain constant and give you a good and stable spectrum to work with. One of the nice features we'll show as well too is the fact that it is very interconnected. It does have Wi-Fi options and the ability to email those results right back or for reach back purposes and to get other feedback on those analysis quickly while you're still in the field. And the newest part is this ISOCS characterization and Genie compatibility. And that's what we're going to focus about the second half of the presentation on here on today. Okay. So first, a little bit of history. The Inspector 1000, some of you may have been aware of this. This was a really, really popular device that we released, and to be honest, it still is pretty popular. It released about 16 years ago, and some of the feedback that I've heard before is that it's a handheld spectroscopy for the scientists, meaning that it does more than a classical RID device might do, and the fact that it really does that quantification and even the uncertainty on that quantification. So you can get those details and the kind of spectroscopy they're required that you'd want to do for a really extensive analysis of the measurement that you're looking at. A couple of years ago, our colleagues in France released a product, the SPIR-Ace, that used a lot more modern technologies available today, such as integrated Android applications. And that incorporates a lot of features that we'll see here today that help make that handheld device really good and have a lot of great usability and other interconnectivity applications. So, you know, if you remember, so Canberra and Mirion joined a few years ago, and that gives us a lot of really great opportunities. And this is one of them because, you know, we being legacy Canberra, now Mirion spectroscopy division, wanted to be able to say what kind of new offerings could we give to in situ measurement users. Can we take the SPIR-Ace device that has a lot of really great integrated and modern features and then also bring quantification to it? And that's what we're introducing today, the idea of the SPIR-Ace with Genie and ISOCS compatibility. They're calling GenieXport. A little bit about the concepts behind the SPIR-Ace and why this is so new and modern and exciting. The gamma and neutron detectors, if there's an option for a neutron detector here, are directly integrated in the device, making the entire unit itself really compact and lightweight. In fact, it's a little bit smaller than the Inspector 1000, very easy to hold in your hand. The nuclide identification on board is very quick, using algorithms that process the spectra quickly and give you a feedback quite readily for that. The user interface is very similar to other Android applications that you might be used to. And so in that way, it becomes extremely intuitive for a user to easily be able to operate and get from one function to another. One of the nice things about the screen itself is that it's actually very, very bright, which means that it's very easy to use even in sunshine and outdoors and have complete readability. And the ruggedity of that touch screen also means that it really becomes usable for a lot of different applications. The different tools integrated also make that connectivity with Wi-Fi and cellular very easy and give you a lot of different ways to make use of the data that you're looking at. There is also this option called SPIR-View Mobile. We have a picture of it down in the lower right. And this is another layered product that helps take all the data collected from the SPIR-Ace and map it onto a supervisory system as well too. So for rapid response in the field and other emergency response applications, that comes in nice. I do want to comment that the SPIR-Ace is just one of the SPIR product family. We're going to be talking about the small handheld device here today. But if some of those technologies and features are things that you like but don't necessarily have the right application for, I wanted to point out that those same technologies are deployed in a series of other different products of the SPIR family. For instance, here is our SPIR pack, where the detector itself is actually located in the backpack itself. It's quite a bit larger for some increased sensitivity, but controlled by a remote application on the smartphone here as well too, in a very similar way that we'll see with the SPIR-Ace. And similarly, the SPIR Explorer deploys a detector on a mobile drone, so you can take that into some military applications, portal monitors as well too, for that quick identification, and even mounting these devices on helicopters for, in this case, called the SPIR-Ident Mobile. So there's a lot more applications here beyond just the handheld SPIR-Ace itself. All right, well, let's talk about that SPIR-Ace. What is it? So taking a look at here's what the outside of the device looks like. First thing to notice is it does have a nice hand strap, so you can go ahead and hold on to it securely. And it is actually available to be put on both sides of the device itself, so that you can switch your hands if you happen to be left-handed or right-handed. Up at the top here, we have a series of indicators. The bright green one here is our battery indicator, and two smaller ones are our gamma and neutron indicators as well too. So these LEDs will in fact flash when it does detect an alarm. They have an on-off button, as well as a button to manually start an acquisition. A speaker that's going to help generate alarms. We'll see that in a few minutes. If I come on down to the bottom here, I have two different probes, or two different connectors. One here is a port that allows me to connect headphones. So in case I want to be able to directly hear those alarms via headphones rather than the physical alarm, I can use it that way. And then I also do have a port for an external probe here that allows me to connect an external alpha beta probe in the case that I need to use some for some sniffing applications. On the reverse side here, I do have a battery enclosure. It does have a long battery life for our operational day. I also meant to point out here that we do have a option to put an SD card in to store that data. And it has some pretty tight screws there, so it's not easily removable. And finally, on the right-hand side here, I have a micro USB port. And this is how the device is primarily charged via plugging into either a mains power supply or even a USB port on the computer. And we'll also use the same port in order to connect directly to the computer and access the files inside the device as well too. Looking inside the device, the gamma detector is located right in this top region here. It's covered in a rubber or a silicon boot here for some increased ruggedity. The options that happen to include a neutron detector will have a lithium zinc sulfide tube and a moderator along the right-hand side here. And then it also has a GM tube integrated inside, so when it's measuring dose rate at a higher range, it'll actually switch over and use that GM tube. And the entire device is pretty light and easy to hold here. So let's look at how we might go ahead and start using that device. Excuse me. So there are really 4 modes of operation to talk about when we start breaking down how somebody might want to use this device. The way I like to go through that is starting with passive detection, using the device to be sensitive to the presence of radioactivity. Once that radioactivity is alarmed or detected, how do you locate where that radioactivity is coming from? And we'll use some search and locate functions to do that. Once you find the source, the next step is, of course, to figure out what kind of radioactivity are we looking for. And that's where we're going to look at this really quick and fast onboard algorithm to identify those nuclides. And finally, the most exciting part for me is quantifying that activity using the GenieXport functionality and ISOCS to not only identify those nuclides, but now also quantify them and be able to use them for reporting and other decision-making purposes. So I'm going to switch now to my camera here. We're going to look directly at the SPIR-Ace. And so my first step as I walk through, is we're going to go ahead and make the alarm. I'm going to ask my moderator to bring my source for me, please. So what we have here is a cesium-137 source that we can use to help create that alarm. This is about a 0.25 microcurie activity. And so what we see as we bring it over here, and actually before I bring it over, you notice the device looks like it's off, but in fact it's just in a low power mode. The screen is dimmed to preserve power, but as soon as I bring the source nearby, it's going to turn into a detection mode and alarm on the activity of that cesium source. A few things are going on. First, you see that the color went yellow to indicate detection. I'm going to pull my mic a little bit closer so that you can hear the alarm, the audio alarm, as well as the vibrating on the table itself. Now I'm going to go ahead and neutralize that alarm so that we can continue our conversation. You see on the bottom here that we have a scale here to indicate the dose rate. As I went into the yellow mode, the detection mode, we saw that increase here. Up in the upper right-hand side, we see the reported dose rate in micro-R per hour. And if we had a neutron option as well, too, we would see that shown right in the top header as well, too. So if we add a second source here, we can see that this is going to then increase the alarm level, and we'll see the dose rate increase until we come right up into a higher alarm state. And in fact, if we continued applying some additional activity, we would go then into a warning category as well, too, and move into this even darker red. Now, these settings are these thresholds are user definable as well, too, so you can customize those for what you need to do. I'm going to take these sources back. So then the next step, after I've identified that there is some activity, is to help locate where that was occurring. And so I'm going to switch to my next mode by a simple swipe feature. And this gives me my time series that shows me my count rate over time here. So the green here, again, indicates that it's currently measuring, but does not detect any significant amount of radioactivity. And we'll see as I bring the source closer that as it approaches, my count rate increases, my detection alarm signal, and we'll see that the observed count rate, again, increases over time. As I take the source farther away here, we're going to see that it will drop off. And so in this way, I get a really nice time visual of activity or observed dose rate over time. So you can imagine that could be useful for a lot of different applications, whether the person itself is walking with the device as they're approaching the source of activity, or even if that source of activity itself is moving, such as a person carrying some sort of contaminant or a truck or other vehicle moving. Any sort of transient analysis here. Another really nice feature in helping to locate this is my radar screen here, where it shows a history of the observed count rate depending on where the device has been. So it's a little bit tricky to show on this with the cameras here, but we recorded a video to demonstrate this purpose. Okay. So in this video, I'm walking with a SPIR-Ace on my hands, and we've set up a trash can that has a source located inside. As I approach that trash can, you can see that the activity is demonstrated in the radar screen here. As I rotate left to right, we see it continues with the memory of where it is. And then once I'm able to go ahead and actually find that source within the trash can itself, it does alarm to red, and it keeps helps the user identify where, with respect to the user, that observed activity was. So that's a really nice feature as well, too. So the last mode that I wanted to show you briefly related to finding the source is this mapping feature. And so this is actually really cool. When I connect to Wi-Fi or some other way to download these maps, this is actually a big map. And what we see here is our facility in Mirion, Connecticut. This is where we happen to manufacture most of our germanium detectors here in the US. And so the integrated GPS shows us the location of the devices currently. And the different radioactivity symbols here show us where the different alarms occurred over the history of this particular device until I go ahead and clear them. So this is really nice to be able to record for a particular measurement campaign where those alarms have been occurring as the operator is moving around the environment. One of the screens that I skipped over here was the spectrum screen. And so this is where, well, at least myself as a spectroscopist get really excited because this starts giving us that information about what are we actually looking at. Like any typical spectrum, this gives us the energy on the bottom. This goes from 0 keV to about 3,000 keV or 3 MeV. And this is constantly acquiring data until we start initiating a specific spectrum count. So if I take one of the sources here, and again place it nearby, we'll see that the signal alarms again. I'll go ahead and mute that alarm for us. And we see that the spectrum immediately starts accumulating, and I have a peak growing right here at 662 keV, which would be consistent with our cesium-137. And it's a little bit hard to see with the camera here, but there's even a small peak indication or peak label that this is cesium-137 possibly. And so there's actually two ways to initiate a count. If you've configured the device, it can actually start a count as soon as an alarm occurs, so it's an auto count. And in this case, we've configured it to start on manual counts only, which means that I can go ahead and select this confirm identification button, and it's going to start a count directly. This progress bar here shows me the length of that count as I'm completing. I believe this is calibrated for about a 30-second count here. Down on the bottom is where that rapid identification is occurring. So I have proposed a cesium-137 count, and in fact it gives me a confidence value of 10, which means that the algorithms are really confident that cesium-137 is the nuclide being observed here. The scale here ranges from about 1 to 10, or anything above 7 is high confidence. I also see the indication here, IND for industrial, and this gives me a categorization of what kind of nuclide cesium is. There's a few other features here that we'll go into, or make sure to point out. So for instance, this reads, here we go, it finished that count and resumed. It reads nuclear power plant here, which means that the current library being used for that analysis was the nuclear plant waste category. It's possible to go ahead and change the library used for that rapid identification to be a little bit more aligned with your application. It also says that background subtraction is currently occurring. So this device is designed such that you can acquire a background ahead of time, and that automatically gets subtracted to increase the accuracy of that nuclide identification as well too. Okay. So if I go ahead and review that count, I'm going to open my settings menu. There's a few different options here, including history, data log, alarm indicators. It also has a login for administrators. So we're going to go ahead and access that history and take a look at that count that occurred. So on the top here, we have event 181, and this gives me some of the more details about that 30-second count we acquired. What I see at the top first is that it gives me some header information. It talks to me about the duration of the count, the GPS coordinates of that count itself, the temperature of the device, both the maximum gamma rate observed during that 30-second count and the average gamma rate, and some additional information as well too. So I have the spectra viewed here, which I can go ahead and zoom in on as well if I like. Now this is really useful because I can go ahead and align these cursors here to focus in on the peak, and I can get some nice information to validate the quality of the spectrum. It gives me the value of the left and right channel, and then also what the centroid located here is at 660 keV. So that's pretty close to our expected 662 keV, especially for a sodium ion detector. A few other pieces of information. I can come to my peak section here, and it gives me a recording of all the identified peaks within the spectra that were used for that identification algorithm, as well as the map itself of the location of that event. And then finally, the text button here, the last one is one that introduces some of the new features that we use for the GenieXport to help transition this from a onboard identification algorithm to a full quantification for nuclide identification. Okay. So I'm going to go ahead and return back to the beginning here, and we're going to demonstrate how we're going to do that measurement for a measurement on the device from beginning to end of how we are going to quantify some radioactivity. So the first step that I want to do is I want to adjust the count time such that it's a little bit longer so I can get some really good statistics so that I know that I have good data to get the most robust answer that I can. So I'm going to return back to the settings menu. And in this case, I'm going to come to More. And I'm going to select, in this case, Spectrum Acquisition. And I notice there is a lot of features here as well, too. We won't go into many of these today, but I just do want to point out that there is a lot of functionality here. Within Spectrum Acquisition, I'm going to come to my end condition time, and I'm going to increase that from 30 seconds to about 5 minutes here. So I can use the scaling bar to get it pretty close, and then use the plus and minus to do the fine adjust and apply this. Returning back to my main screen here. And now I'm going to select, oh, I almost forgot to put my source in place. So I'm going to put my, my 0.25 microcurie cesium-137 source. Again, I'm going to put it right near the end cap here, a little bit outside the view of the camera, but such that it's in a reproducible condition. Then I'm going to select Confirm Identification to start that count. As we saw before, we're going to see this progress bar in light blue starting. This is about a 5-minute count, so we'll leave that collecting for a few minutes and come back to it when it's done. Okay. So one of the questions that I sometimes get asked is, how can I use this device in applications where I cannot easily access, or perhaps I don't want the operator near that source of radioactivity? Is there a way that I can initiate a count and have the device, specifically the detector, the sensor, closer than I want my operator? And the answer is yes, there is a way. And we call that the remote start capability. And here's the key. We mentioned before that the SPIR-Ace is connected. It has the ability to connect to Wi-Fi and other things. And so as long as you have a Wi-Fi in the area, or even just use your cell phone to create a local hotspot, you can connect the SPIR-Ace to the local hotspot, and then connect a remote computer, a laptop, a tablet, something else of that nature, to that same network. Within the SPIR-Ace, it has this function called remote display, and this is actually a screen that's taken directly from that application. And the remote display provides a web IP address, in this case 172.29.12.162, that when you type into a remote browser, it's going to bring up this screen called the remote display that will enable some controls over the SPIR-Ace device from the remote computer, as well as view the acquisition and progress and some other information like the dose rate. So we demonstrated this the other day, and I'll show another video to illustrate how this might work. So before I begin into this video, I want to point out a few things. So this is me. I'm sitting on a bench with this computer, and I've connected this computer to a hotspot using a phone here. And then I've also connected to the SPIR-Ace to that same hotspot, just as we described in the previous slide. On this computer, I typed in the IP address of the remote display of the SPIR-Ace, and this screen here shows the screen I'm looking at on my lap here. And what I want to look at is when I select the Confirm Identification button on the remote display in the web browser here, we're going to see the SPIR-Ace light up and initiate that count based purely on that click here. So let's go ahead. You see my mouse come along and hit start. The device lights up, and initially we see a count coming in. We see that same light blue progress bar occurring like we did in the device to my left-hand side here. And that's mirrored by the progress bar on the web browser itself. We also see that the count rate on the SPIR-Ace, or the dose rate here on the SPIR-Ace, is mirrored as well by the dose rate on the remote display. And so I can use this for some really good information. Is the dose safe enough for an operator enter, or do perhaps they have to stop? And you can imagine that this allows a lot of good functionalities. You could now mount the SPIR-Ace, for instance, on a truck or other mobile cart, move it into a dangerous environment, and start it in the same way. Or even if you didn't quite have a good angle to start that count here, you could go ahead and position the device where you need to, perhaps out of reach or on a crane, and then do the same sort of functionality here to be able to initiate that count and record those results. And you do have the option to extend the count or resume, like we saw on the device, in case we didn't quite get enough data in that time where we want to extend that count. So that's pretty nice. Okay. So I'm going to return back to my camera here. We can see that my device is almost done. It continues to monitor, excuse me, it continues to measure that source that we placed, and has, in the meantime, confidently identified that we are in fact seeing a cesium-137. So as we come to the end here, we now have three buttons selected. The first one says Resume, where it can actually double the amount of count time. The second button is Analysis, and we're going to go ahead and select that one now. So this brings us directly up to the event detail that we saw on the previous count. And we have the same options as before, where we can go and do some spot checking of the information collected. But we're going to jump right to our text button and enter in the information here. So first I have a pencil icon. And this allows me to enter in some information relevant to the count, simple text string. So for instance, we might want to say that this is a point source, and I think we have the number 1505 labeled on the back of this, so I can use this for some record keeping. Okay. And then I also have the cube icon, and this is key because the cube icon brings us to what we call geometries available. And so what we've done is we've created a series of efficiency calibrations using ISOCS and an ISOCS characterization of the detector. And we'll go into a little bit more detail about what those are. And we've created a series of these calibrations and loaded them up to the device so they're very easy and quick to select. They're then going to become part of the spectrum that we've calibrated, or that we've collected. So it's a little bit tough to see here, but I'm going to go ahead and take point source at 0 centimeters. That's pretty consistent with our geometry. I'm going to apply that. Then when I hit event, or when I exit the screen, you'll see on the bottom here it says CAM conversion success. And that means that the GenieXport application has done its job, which means at the conclusion of the count, the SPIR-Ace app creates an N42 file, and then the GenieXport file takes that file and converts it to the Genie formatted CNF or CAM file. And that's going to have embedded in it both the spectral data, including the count time and the counts and all the other information we need with the spectrum, as well as that text string. So I have a record of the sample information to help identify it for me later. And also that embedded efficiency or geometry file. So I can very easily go ahead and collect that, analyze that measurement when I do have it on my Genie system. So the next stage I'm going to do is I'm going to take this device and I'm going to connect it with my USB directly to the computer. Now there's a few different ways I could do this. I could also do it by email, but in this case I'll directly connect it. I'm using my micro USB. I'll connect it into the side, and then I'll also connect the other side to the USB port on my computer here. There we go. So now I'm going to Windows Explorer. I'm going to open Windows Explorer and look at the SPIR-Ace device. That's TX6U08 or 8033 for this particular unit. And within the internal storage of the SPIR-Ace, I have a folder called SPIR App. And this has my GenieXport data into it. And so what it's doing now is pulling the SPIR-Ace for all the spectra that I've acquired. You'll see that for each event, event 58, event 68, et cetera, it also has an associated background. So I mentioned earlier that the SPIR-Ace can have a background subtraction used for its algorithm. And so within the GenieXport application, the way that works is that each event CNF will also have a background CNF so that you can do a manual background subtraction in Genie if you so like. Okay. I'm just scrolling here to be able to access my desktop. So I'm going to take this last event, event 183, and I'm going to drag and drop that onto my desktop such that it's off the device and easily accessible. All right. And then I'm going to double click this, and it's going to launch directly into Genie for me. Here we are. And so again, I see my 662 keV peak. For those of you who may not have seen Genie very much before, just a few words. It is a very powerful laboratory quality analysis software package. It's been standard for 20 or more years, and very common to see this in different laboratory applications and to be used for reporting of nuclide activities and quantities with high accuracy and defensibility. The Genie software has a lot of different analysis capabilities, so they really let you fine-tune those analysis to really optimize it for your particular application. And so in this case, what I like to do is I like to create a few shortcut tools right at the top here, such that I can quickly look at the features that I'm interested in. So one of those that I want to do initially, once I've opened it up within Genie, is check to make sure that that efficiency actually did copy over, and I can see here that it did. So this is the efficiency calibration associated with that point source at 0 centimeters that I selected on the device. You see it's been directly embedded and already part of the spectral measurement. I can also open up the sample information to verify that the description is in fact entered. You can see I had a little trouble spelling source, but I think you see the idea here. And then finally, I want to go ahead and actually do that quantitative analysis. And so I've programmed an ANSF to automatically go through and do my peak location, my peak analysis, my efficiency correction, and finally my nuclide identification, all in one step here with reporting. And so since I already had the efficiency calibration associated with the device, I see that this came out in just really a click or two to get that result. So as I walk through my report, I see I have my primary header information with that key information as we discussed. As I scroll on down here, I now see my peak analysis report, and I see my peak centroid observed here. Here's my 672 keV peak, pretty close to that 662 that was identified, and my peak counts and uncertainty in those peak counts. So I continue on down. Now I have my nuclide identification section, where I see that it has constantly identified cesium-137 with a confidence of 0.94, identified the energy at 661, and calculated the activity to be 0.97 microcuries, which is pretty darn close to my 0.25 here. Additionally, I see my activity uncertainty being calculated as 0.017, and so I have that as part of my record and for reporting as well too. And so that's from beginning to end how I can get my full quantification information. So I want to take this opportunity to talk a little bit more about the ISOCS portion of this analysis. So to me, there's really three parts of the ISOCS methodology that bring the entire system together. The idea that we use a highly accurate and defensible ISOCS characterization, and that's why I have displayed in this icon here over the right-hand side. For each SPIR-Ace model, the sodium iodide versus the lanthanum bromide, we actually develop an efficiency mapping at different energy levels at different distances from the device, so that we can use this in the following steps. The second part of the methodology here is the geometry composer. Now I'll show you what that is in a few moments. We have a few examples below. When I discuss ISOCS, I use ISOCS and LabSOCS a little bit interchangeably. They are in fact two different applications. And really the difference here between those products is that the ISOCS software and really the ISOCS templates within the geometry composer are targeted for applications you are more likely to see in the field. These could be a tank or a cylinder or a drum with a hot spot inside, a complex pipe over here, for instance, where the LabSOCS templates tend to be ones you're more likely to encounter in a laboratory environment, such as a simple box on end cap, a filter paper, a Marinelli beaker. And so these are all user-driven templates such that a user can define their particular measurement geometry pretty quickly and with these few steps. And then finally, using the third step, the ISOCS efficiency calibration engines, which combine together that mapping of the efficiency of the SPIR-Ace device with the user-defined templates. So there's a few different ways that the SPIR-Ace can make use of this. The way that we did it in the first demonstration here was actually with a preloaded calibration. So the screen that we saw has some geometries available. So for instance, we had selected point source at 0 centimeters, which is the geometry that we made ahead of time and then loaded into the device itself. So I could select it and have it available for me. And so that might be something very similar to this. In fact, here we show the next one, the point source at 25 centimeters, and a few other examples here as well too. So for instance, demonstrated here is a filter paper on end cap. One of the more interesting ones, I think, is this pipe. And in fact, this is the legacy Spectral 1000 unit. As we can see, it's measuring a pipe in an environment here, probably for some hold-up measurements. And on the right-hand side, we can see how we can model that with Geometry Composer and create a very similar geometry for that to create my efficiency calibration. Some other applications, and these are actually germanium applications, but you can imagine that the SPIR-Ace can be done in a very similar way, such as measuring of the ground or of a manually beaker or even of the drum. And so let's for hypotheticalness sake, imagine that the measurement we just made was with a drum. How would we go ahead and make that change? How would we analyze a spectra with a drum measurement? So I'm going to return to my spectrum here and adjust and create a new efficiency calibration, assuming that the spectra in fact did come from a 208 liter drum. So I'm going to launch Geometry Composer from my options menu. And when I'm in Geometry Composer, I'm going to work through a few steps. The first one is I'm going to identify a user template that most closely matches the geometry that I'm interested in. So as I described before, I have the option for either ISOCS or LabSOCS, depending on which package I have available to me. And I'm going to find the one that would make the most sense in this case. Simple cylinder is going to be a good choice. I'm going to open that up. Next thing I need to do is I need to identify which ISOCS characterization is appropriate for this one. As I scroll on down, I see I have SPIR-Ace for sodium iodide detector. And I can change the body style to help make it something a little bit more appropriate. Now this is just a physical or visual rendering of the body. It doesn't actually make any difference for the algorithms, but it makes them nice to see how this all works together. So now I'm going to create this efficiency, or create this geometry. The way Geometry Composer works is I have a series of dimensions here, dimensions 1.1, 1.2, 1.3, and they each correspond to a physical parameter of the template. So for instance, 1.1 here is my wall thickness of the cylinder or my drum. 1.2 here is my inside diameter of that cylinder, and 1.3 here is the total height. So I looked up a little bit ahead of time what the dimensions of a standard 208 liter drum might be. So for instance, the wall thickness might be about 5 millimeters thick. The diameter typically is about 572 millimeters. And then the fill height, or the total height, about 851. I identify what material that might be. So for instance, stainless steel. And then this way I continue on through the rest of the parameters. I'm going to imagine that this fill height, the fill height of the source, is almost completely full, 800 millimeters. Give it a lower density matrix, perhaps just simply water here, and identify it to be 100% relative concentration. I can apply this, and we see here that I have a physical rendering of a drum that's consistent with a 208 liter 208 liter drum. I can make the container here transparent so I can see the activity inside and verify that. So we did a pretty simple one here, but there's a lot more complexity you can add, such as different fill heights, hot spots, different matrices, whatever's necessary to adequately represent your measurement geometry. I can go ahead and move this detector back a little bit too, if we need to do that. So I can edit my dimensions, and let's move the detector back about 10 centimeters. Here. When I'm confident that I have adequately represented my geometry, I can save that as my drum, validate that all the parameters were entered without any overlaps or inconsistencies, and then finally go ahead and say generate my data efficiency points. This is where it goes and calls those ISOCS algorithms, the ISOCS characterization, to make a specific efficiency calibration file that's unique to that particular detector and that user-defined geometry. Now I return back to my, my Spectrum in Genie. I apply that calibration by going to efficiency by ISOCS and LabSOCS. And I see that it gets pre-populated with that geometry that I just created. I can take a quick look at the curve that it creates. I usually recommend to use interpolated for ISOCS and mathematically produced calibrations. And we see I do, in fact, have a good curve generated. And then finally, I can apply it to the calibration, or to the spectrum. When I repeat my analysis here, it's going to use that new and updated efficiency calibration. As I scroll on back, I can now observe that the new cesium-137 has been calculated to have a higher activity, about 160 microcuries, which would be consistent because now I'm assuming I have a much larger geometry, and that same detected gamma rate now would be associated with that. And so I can take the same concepts that I did here, and I can actually save a new calibration file and load that right back into the SPIR-Ace device, so I can have that as a selection on board if I need that as well too. So we're not just limited to those predefined ones that you already find on the device. Okay. So we've covered a lot of concepts here in the past hour. We've talked about the usability of the device itself, the ability to make detection alarms and to do some searching for the searching for activity, the onboard nuclide identification. It does have the ability to stabilize with without a source to make sure that gain stays constant, and we can use that for good quantitative analysis consistency. We talked about how we are able to easily have that data transmitted back via its remote connection. There's a lot of other things that we did not talk about, so there's a lot of features. I encourage you to check out this link here where we do have posted a spec sheet on our Mirion.com website. And what I'm most excited to do is to show you some of the functions about how this GenieXport now can be used to take this really handheld RID device and make it into a true in situ spectroscopic quantitative instrument. I'm gonna pause here now and wrap up and see what kind of questions you might have. One question we have is, can you access and modify the nuclide library on the device? That's a great question. There's about 7 different nuclide libraries on the device. You can create custom libraries using those existing nuclides on there. And so with over 80 nuclides on the device, it really has all the nuclides that we could imagine you might want to use to do that onboard analysis. And if you need any more, you can always come out into Genie and do the analysis there as well too. Another question we have is about the neutron detector option. So the SPIR-Ace comes in 2 models, the one with gamma and the one with gamma and neutron. And so the ones with neutron will have the probe right in the back side here that is integrated in the device, and will also help alarm on the front with neutron detection. That's absolutely an option as well too for purchasing. Another question here is about the option to have users manually correct the peak energy location as they may become shifted for humidity or temperature. That's a good question too. So that's one of the features I did not cover. The system has the ability to do a gain adjustment. really. So this becomes especially important for longer-term shifts. In short term, the self-stabilization works very well. In longer term, what we typically recommend is using a cesium-137 source or other check source. And the auto-calibration option is going to work through a series of routines where the user will specify which kind of nuclide they are looking at. So for instance, cesium-137. And then the software will adjust the gain to bring the expected energy calibration right back to where it should be. And so that's something that we recommend doing really in the beginning of any given measurement campaign. And it works pretty well. Okay. Another question we have here is about how the background subtraction works. That's another very good question. So the background subtraction, the user actually has the option to have that both be enabled or disabled. In the case when it's enabled, the first step is just after a gain calibration or whenever beginning a measurement campaign, you'll initiate a background count here. And the background count then gets applied to the active measurement. So it'll always be the background that's going to be used until the user goes ahead and defines a new one to be done. Once it's in there, then the rapid NID algorithm incorporate the set background to be part of its algorithms. There's a little bit more detail to that, and to be honest, I'd table that for a little bit after this discussion, but it does integrate in that way. For Genie, what you would do is you would actually go ahead and during that analysis within Genie, you'd specify a background subtraction step and then reach out to that different CNF file that we showed being exported from the Genie application. So another question we have is, does it work without network connectivity and GPS? Sure does, yep. So the device itself is an integrated Android, so like many other Androids that you might be familiar with, you can go into the settings and manually disable all of those. The device absolutely does not need them to do all the functionalities. There will be some features that you'll lose. So for instance, the mapping capability obviously will not work very well with that GPS turned on. And if there's a need where the device needs to have a hard-coded to not have those as well, that can be a special order to have the device come with those physically disabled as well too. Guys are getting so good with all these questions. Thank you. Another question that we have is about the Inspector 1000. Is it still available? It is, yes. So the Inspector 1000, even 16 years later, is still a product that we have available. And so please don't be shy if that's something that you're interested in as well too. I think that these two devices really do a great job in offering different benefits in the in situ handheld spectroscopy applications. Great. Another question here. Does the ISOCS geometry efficiency have to come from SPIR-Ace, or can it be used from the Genie computer? Well, I think I understand this question, so please let me know if I'm misunderstanding it. What I demonstrated today were two different ways. One was the ISOCS calibration coming preloaded on the device, and that's where I selected the point source on the device that then became part of the spectral record and was incorporated directly within that CNF. The second way that I did the activity calculation was that I made a ISOCS efficiency calibration on the computer and applied that to the spectra after the fact. So the ISOCS geometries, we do include some of them that are preloaded in the device, but if you wanted to do the second method, which was if you wanted to create an ISOCS geometry that was not one of those preloaded options, but you wanted it to be a preloaded option, that's a very easy process as well too. And so it requires a little bit more setup. What you would do is you'd create the calibration. So for instance, the drum calibration on your computer, and then you make what we call a Genie cal file, CAL file. And then you'll use your same USB cord here to actually load it back into the SPIR-Ace and put it within a specific location in the SPIR directory. And then it becomes an option right on that geometry is available as well too. So the answer is yes, yes, you can do both ways. Another question we have here is how long will the device operate for full charge? There's a few different things that depends on. We mentioned earlier that it does operate in a low power mode. That means that the device display will be turned down until an alarm occurs, and that's going to have a slightly longer battery life, as long as 11 hours. If you are operating it more constantly and continually using it for operation, is about 4.5 or 5 hours that we expect to see it. So depending on the level of activity, 4.5 to 11 hours. Good question. Another question here that we received is the device waterproof? Is IP65 water resistant? Okay. Well, we'll stay online for a few more minutes here if you have any more questions or comments. Again, I encourage you to go onto our website and review the specifications that we have available. I do appreciate you very much for signing in today and asking the questions and the interest that you provide. Again, my name is Kara Phillips. I'm product manager with our Mirion Spectroscopy department. And I'm excited to bring this device to you along with our Mirion HPD division as well too. Thanks again, and feel free to continue adding some questions. We look forward to answering them after the seminar.